Okay, so let's start. So for this second presentation, we're going to do a short tutorial on some useful VUnit primitives and what you can do with them in terms of design patterns and so on. So the starting point for our discussion is that we have the test bench, obviously, and we have a duct, a device on the test, and the thing is that we have multiple interfaces. So in this example, I have an input stream and an output stream, say a stream of packets or something, and we have a bus interface for configuring the ducts. So obviously we need to verify all interfaces and do action on all of them, and we also need to do it concurrently to get a proper verification. So one approach to this could be that let's have one single big process in which we put all our test code. It tends to be micromanaging on a clock cycle level, because you start by, okay, I'm going to put 3 clock cycles with data on the input stream, and then because there is a latency in the duct, things are going to happen on the output, so now I need to also check what's happening on the output while I'm putting new data on the input. So it gets kind of messy very quickly, and it also violates one principle which is good when testing, is that often you don't care about the latency of a streaming device. It's 2 clock cycles or 3, maybe not that important. But in this case, the test bench will depend on the latency. If we add a pipeline stage to improve timing, for example, then we have to rearrange our lines. So that's also a messy thing that you have to do with a single process test bench. And there is no abstraction whatsoever. So one improvement you can do to this is to start using one process per interface. So on the input we have our stimulated generator, which is pushing data into the stream. We have an output process that checks the data that comes out, and we have a process that interacts with the bus interface. Now each process can focus on their type of transactions, like pushing a packet on the input. You don't have to interleave that with also mentioning things on the output. So the abstraction is much better in this case. We're also less sensitive to changes in the duct, as I described before. One thing that kind of makes things worse is that now you have 3 processes. They are spread throughout your test file, and the overview might not be as good as it was before when everything was in a single process. And we also need to solve information sharing. I mean, this guy who needs to test the output needs to know what the input data is. It needs to know what this guy did to configure the device on the test. So we need to share information. So when it comes to information sharing between processes, there are basically 2 main models for this. This is true in VHDL, and this is true in software development in general. We can have share memory models, or we can have message passing models. When it comes to share memory, as the name suggests, we have a common memory. In VHDL, a shared variable or global signal, in which we can write data and we can read data. And any process can do that. And to transfer information, someone is writing into memory and someone is reading from the memory. This is a bit prone to race conditions. For example, if you have one process writing data into memory, expecting, for example, say the input process writes the stimuli data into the memory, it expects the output process to read that data, but before the output process does that, the input process starts writing the next set of data, so it overwrites the first. So typically what we do is that we add a lot of synchronization signals, like Boolean signals, and we call them start and stop and ready and lock and so on. And it tends to become quite a messy spaghetti code after some time. So this doesn't scale very well as the number of interfaces and the number of processes grows. So a cleaner approach is to use a message passing model. The difference here is that at any time there is only one process that owns the data, and only the process that owns data is allowed to access data, read, write. Of course, we still need to share data, and that is done by 2 methods. One is that we take a copy of the data and hand it over to another process. What you do with that data doesn't affect me because it's a copy. Or we can hand over ownership. Think of a pointer into memory or a reference. I can give you my pointer, and now we share memory again because we're both pointing at the same data. So the important thing for handing over ownership is that I also delete my reference. So I should have no access whatsoever to the memory that I handed ownership to. So generally speaking, we have processes that are more decoupled, which also means that it's easier to scale this approach. So basic message processing model can be implemented using queues. So transferring information again, queues like FIFOs, we push data into the input and we pop from the output. So sharing information through copying means that we push some data in, like the integer 17, and on the output some process pops the data out, getting a copy of that 17. So we have two integer values. In the pointer case or in the reference case, we can push and pop the pointer or reference, but the act of pushing a reference into the queue also means that that reference has to be deleted or nullified when we do that. So when it comes to VUnit and VUnit queues, there are basically two things you need to know. One is how to create a queue, and you do that by declaring a constant there. Queue is of queue type, and the initial values you get by calling the new queue function. So that's a function without any parameters into it. And the second thing you need to know is that VUnit queues are kind of unique in the way that they can handle multiple types. So you can mix types within the same queue. So I can push in an integer, and I can push in a standalone vector, or whatever. It doesn't mean that we're not type safe. So if during runtime, say you push in the integer 17 and then you try to pop out the boolean, you'll get type error. So it's still type safe the way we want PHDL to be. So now if we put this into our, as I said, we can also push and pop references. And for example, VUnit has a type called integer array type, which is a dynamic array, which is one-dimensional, two-dimensional, or even three-dimensional. So it can be used to store a packet or an image, for example. So this is an example of something that can be large, just we don't want to copy due to performance. So we can push and pop references to this memory instead. And to be explicit that this is what we do, we talk about push ref or pop ref procedures and functions instead. And the difference with a push ref compared to normal push is that the array we put in, the reference, the pointer, is nullified. So after you've done this call and you return, there is nothing in this array variable. And you can no longer access that memory because you have handed over the ownership. Of course, sometimes you want to have your own copy of the array, but then you have to make a copy of it explicitly to show that you actually know what you're doing. So let's put this into our test bench. So now we have our stimuli generator on the left. We're applying input stimuli, and when we do, we also push that data into our queue. And on the output, we have our checker process that verifies the output. So the first thing it does is it waits for the queue to be not empty. That is, something is in the queue. It does that every clock cycle, so it's pulling the queue basically. Once there is some data, it will pop the queue for data. It has some prediction function to figure out, given this input data, what do I expect on the output? And I simplified everything here. I'm just talking about the input and output. I'm kind of ignoring that we also have a configuration bus that can also be a piece of the puzzle. And then once I have the expected data, I can wait for the output. Typically, maybe I have some output valid signal that I want to become 1. And once I have that, I can verify and check that the output data equals what I expected. And then I go back to the top, pop some more data from the queue and continue. A problem here is that I'm polling the queue every clock cycle. So there is an implicit latency of 1 clock cycle in every iteration. And that can be a problem in some test cases. So in order to get rid of that extra clock cycle, we can start using something called VUnit events. So some terminology, VHDL has something called an event. So if I have a wait statement, for example, wait until my start signal equals 1, it means VHDL waits for some change in that signal, and when there's a change in the signal, it checks is the signal value 1. If it is, it unblocks. Event in general in computer science means something happened. And in VHDL, it really means something changed. So I have the same signal, and I assign true to it, if it's a Boolean, and then I assign true to it again. You can think of it as 2 things happened. But VHDL will only see 1 thing, because it's only the first assignment of true. If it was false from the beginning, that changes the value of the signal. So that can give some subtle bugs sometimes. So what we tried in VUnit was to create a more abstract event concept, which also allows us to add some other features, like we can log every event that happens in the system. So afterwards you can look at the log and debug if you have some problem. There are built-in events, for example, run a timeout. This is an event that happens if you have a VUnit watchdog. The watchdog is supposed to time out and fail the test bench if it takes too long time, that is stuck. Just before it times out and gives your error message, it will also activate the run a timeout event, and we'll see later on how that can be used. But the important thing, there are built-in events, and you can also create your custom events. And that's what we're going to do for our test bench. So you create an event, it's always a signal, because we're still going to use the wait statements in VHDL, which works on signals. So I create my event, it's of event type, and I call the initialization function a new event, and I'm also giving it a name, it's a string. If I want to signal that the event has happened, I use the notify procedure. And there are basically 3 ways for someone interested in that happening to figure out that it has happened. You can either do wait until it's active on the event. Simply it will wait and unblock when the event is activated. You can also use the isActive message function, same thing, but then you also provide a string, which is the log entry in your log if you want to debug later. And then on the last line, we have something called the log active function. This is a bit special. So say you have your test bench, you have your VUnit watchdog, it times out, and you get a message, oh, there's an error, your test bench was running for 1 millisecond. Obviously, you're going to ask yourself, why did it time out? So you have your test bench, there's a bunch of wait statements, and most likely some of those wait statements are stuck, but you don't know which one. So what you can do, for example, if you have on the output, I'm waiting for output value to become 1, this is a something, I can add or log active runner timeout event coming from the watchdog, and then I provide a text. For example, I'm sitting here waiting for output value to become true. So what happens now is when you run your test bench, you have a timeout, the watchdog will activate the event. The event will wake up this log active function, which will print to the log, I'm waiting for output value. The log active function always returns false, so it will never affect whether or not wait statement blocks or unblocks. But the difference now is that when the simulation terminates with a timeout error, you can also see which of our wait statements are sitting waiting for something to happen. And that can be a good cue for figuring out what's wrong with the system. that communication delay we had before. So rather than polling the queue every clock cycle, we simply check, is the queue empty? If not, we sit waiting for the event. And we also created the event down here. And also, when we push new data or a set of data into the queue, we activate the event with a notify procedure. But the remaining piece of the dot checker is the same as it was before. There's a problem with this test bench. The problem is that quite commonly in the test benches you have your stimuli lead generator, which is also the main process of the test bench, which eventually will call our test runner cleanup procedure to end the test bench. So typically you do, okay, I'm going to apply all the stimuli input, and then when I'm done, I'm going to finish the test. But be aware that since there is latency typically in the DUT, there is a time from you apply the last input data until it appears on the output and you can verify it. So you cannot terminate the test bench immediately. Okay, so I wait for like 3 clock cycles, or maybe make it 10 just to have some margins. Isn't that good enough? No, not really, because you can have a major flaw in your DUT which prevents it from generating any output data. So the first thing you put into the queue will wake up this checker, and then it will get stuck waiting for output data valid. The stimuli generator will continue to apply inputs. It will put all of those inputs into the queue, but nothing stops it from terminating the test bench after those 10 extra wait cycles. So we need something else to prevent this case. And it's kind of common that you actually end your test bench without actually having tested anything. So it's a silent pause, sometimes called. So we need to introduce locks, and we need to introduce phases. I'm going to speed up a bit because we're a bit behind, but phases is something that happens in the background of the unit. The unit goes through phases as your test bench runs, and you don't see that. You need to know about the test running cleanup phase. This is the phase we enter when we call the test running cleanup function procedure just before we end the simulation. Now, between every phase the unit goes through, there are 2 gates. An exit gate going out of this phase and an entry gate going into this phase. And on gates we can put locks. And if we put a lock on a gate, we prevent the unit from continuing through the phases. We do that by, in our process, to create one private key for ourselves. So here I'm creating a key of key type, and I get the key to the entry gate of the test running cleanup phase. Now I can lock that phase, and obviously can also unlock that phase. And the unit will only continue when all processes that have locks on the gate have unlocked the gate. So in our case, we're waiting for data in the queue. As soon as there is some data, we have been given a task to verify something, and we're going to say that I'm not allowing the test bench to stop before I've completed my task. So I'm going to lock the test runner cleanup phase with my key. Once I've verified the piece of output, I'm going to check, is the queue empty? If it is, well, then I can unlock, and it's okay for me to end the test bench. If it's still new items in the queue, well, I'm going to keep my lock and not going to unlock it at this point. So this is how you can avoid this problem of premature termination of test bench. Here's some summary of what we have discussed today. One process per interface is something that enables us to have a high level of abstraction, and we can also create a test bench which is less brittle to changes in DUT. We've discussed message passing versus shared memory models, and my claim is that, or it's not only my claim, that message passing is less error prone and scales more efficiently than shared memory models. We can implement basic message passing with queues. Specific to VUnit queues, we can mix data, still being type safe. We talked about events as a way to have zero communication delay with synchronization, and it can also be used for things like having wait statements tell you that I'm stuck waiting for something when we have a watchdog timeout. And we also discussed locks as a way to avoid the mistake of a premature termination of test bench. If you want to know more about this, I recommend reading 2 blogs on the VUnit homepage. It's called VUnit Events and VUnit Places. It will go into more detail than I had time to do here today, and also give you some more use cases for when and how you can use these features.